Usually when we talk about like learning a new skill, there's always this terrifying moment of transition.
Oh, for sure. The moment they take the training wheels off.
Exactly. Like you spend months in a flight simulator studying the physics, memorizing the dashboard dials. You get entirely comfortable with the theory of flight. And then one day, the instructor just opens the door to a real Cessna, tosses you the keys, and is like, go fly.
Which is terrifying because the theory is perfectly safe.
Yeah.
Right? It's predictable. But the execution in an actual environment, well, that introduces chaos.
Yeah, suddenly you have crosswinds.
Exactly. Crosswinds, air traffic. But that friction between the theory and the practice, that is where the real rewiring of the brain actually happens.
Totally. And welcome to the deep dive, by the way. In our previous discussions, we've spent, a lot of time in that functional programming simulator.
We really have.
We explored the abstract paradigms of functional languages. We waded through the incredibly parenthesis-heavy syntax of Lisp and Clojure. We learned how to read the dials. But today, we are finally starting the engine.
Yes. Today is where the rubber meets the road.
Right. We are unpacking CS330's Lab 11, the Clojure Lab. Our objective here is to look at the exact concrete mechanisms you need to transform all that theoretical functional knowledge into running, breathing code.
Right. Specifically focusing on data transformations and file processing, which is where this stuff really shines.
Yeah, this is the moment you finally get to see why those paradigms and, all those parentheses actually matter when you're solving a real problem.
It's the payoff for all that setup.
So let's establish the environment first. Imagine walking into a pristine workshop. Your tools are laid out. For this lab, that workshop is your CS330 individual lab work directory.
Which you should all be pretty familiar with by now.
Exactly. You fire up your terminal, you pull down the latest lab files, and your workbench is ready. The Lab 11 Clojure directory drops in, complete with its instructions, and all of your actual Clojure code for this entire exercise is going to live in one single file, lab11.clj.
Just one file. But in this particular workshop, you actually have two entirely different ways to operate your tools, which honestly highlights a core philosophy of Clojure and Lisp in general.
Right. You have the interactive REPL, which you start by simply typing CLJ in the terminal. That's your sandbox.
Yeah.
You type a single line of code, hit enter, and immediately see what it evaluates to. And if you get stuck in a weird state, you just hit Control-D to escape and reset the whole thing.
And that REPL, the read evil print loop, is arguably the heartbeat of functional programming.
It really is.
It encourages this microscopic experimentation. You don't have to write a complete application, compile it, and run some massive test suite just to see if your little rounding function works.
Right. You build the program piece by piece.
Exactly. Validating every tiny assumption as you go. Then, when you've perfected those pieces, you transition to the second way to work, which is running the completed script from top to bottom from the command line using Clojure-m lab11.clj.
But before we put any actual code into that script, we kind of have to address the modern reality of the computer science lab.
Ah, the elephant in the room.
Yep, artificial intelligence. The syllabus for CS330 lays out very specific ground rules for their custom large language model tool, BitBuddy. So we need to talk about how to navigate AI ethically in this context.
It's so important. And the boundaries set for this lab provide a really fantastic framework for your professional development. You are actively encouraged to use BitBuddy to research how Clojure functions work mechanically.
Like a superpowered search engine.
Basically, if you forget the exact syntax for splitting a string into lines or how the conjugate function operates, you can totally ask the LLM for a sample snippet. It acts as an interactive, highly specific reference manual.
But the hard boundary here is that you cannot use the LLM to write the actual logic you're submitting for the assignment. And of course, standard citation rules apply for anything you do research.
Right.
But let's look at the reality of this for a second. If BitBuddy hands me a perfectly working code snippet for reading a file, and I just, drop that snippet into my lab, the line between researching syntax and writing code seems incredibly thin.
It does feel blurry at first.
Right. How do we navigate that without crossing into, improper collaboration with a machine?
Well, the distinction really lies in understanding mechanical patterns versus architectural problem solving.
Okay, unpack that a bit.
So asking an AI, how do I open a text file in Clojure, is like asking a dictionary how to spell a word. You're just looking up a mechanism.
Right.
But asking the AI, write a composed function that rounds a list of numbers, filters out the odd ones, and finds the maximum value, well, that is asking it to solve the specific logic puzzle the lab was literally designed to teach you.
Ah, okay. Because if I ask it to solve the logic puzzle, The AI is probably going to spit out a highly optimized functional solution, but my brain hasn't actually done the work to shift from imperative thinking to functional thinking.
Oh, exact.
I'd just be pasting advanced syntax without undergoing the paradigm shift myself.
You would completely bypass the entire learning objective. Learning functional programming requires a literal rewiring of how you approach state and data flow.
Yeah, it's not just new words, it's a new way of thinking.
And if you use an LLM to bypass the struggle of that rewiring, you might pass the lab, but you will fail to acquire the skill. The goal here is to learn how to be the architect directing the logic, and you use the AI solely to help you look up the raw materials.
That makes perfect sense. So with those boundaries clearly defined, let's actually start looking at the problem the lab presents in part 1.
Let's do it.
The challenge starts with a messy vector of random floating point numbers, ranging anywhere from 4 to about 75. In a traditional imperative language like Java or C++ biz, we would likely tackle this by writing a clunky for loop,
Oh yeah, lots of boilerplate.
initializing a counter variable, mutating some temporary array to hold the clean numbers, using if statements to pick out the even ones.
We would be micromanaging the exact steps the computer takes to iterate through memory.
Right, but functionally we want to build an assembly line, or like a water purification pipeline. We want the data to flow through a series of transformations.
I love the pipeline analogy.
So the first transformation required is rounding these messy decimals into clean integers. We write a simple round function, and then we use the map function to apply it across the entire data set to create roundall.
And map is really the cornerstone of functional data transformation.
It's everywhere.
It is. You hand map a function and a collection. It takes the function, applies it independently to every single item in the collection.
Yeah.
And this is key. It returns an entirely new collection containing the results.
So the original list is safe.
Yes, the original messy list of decimals remains completely untouched and immutable.
Okay, so the next stage of our purification pipeline is where things get a bit conceptually heavy. We need to filter out any numbers that aren't even.
Right.
And the instructions require us to write a curried function called divb, which utilizes a closure to store a factor. We then set that factor to 2 to create our is-even logic and pass that to the filter function to get even all.
That's a lot of terminology all at once.
It is. Let's break down the mechanics here, because currying and closures, they sound like these advanced theoretical concepts, but we're literally just applying them to a very basic math problem here.
Yeah, it helps to look at the mechanical difference between a standard function and a curried one.
Yeah.
A normal division function takes 2 arguments simultaneously, right? The number you have and the divisor you want to check against. You pass it a 10 and a 2, it evaluates and returns true or false.
Simple enough. But the filter function in Clojure doesn't work that way.
Exactly. Filter expects a predicate, basically a rule that only takes 1 argument.
It stands at the conveyor belt, picks up a single number from the list, and hands it to your rule. It has no idea how to pass a second argument like a divisor.
And this is exactly where currying solves the architectural problem. When you call our curry divby function and pass it just the number 2, it doesn't try to do the math immediately.
Because it can't. It lacks the second piece of information.
Right. Instead, it returns a brand new function. And that new function contains a closure, which is basically a persistent memory state where that number 2 is trapped. It's suspended in amber, waiting to be used.
Suspended in amber. I like that. So we hand this new specialized function over to filter. Now, when filter picks up a number from the collection and hands it over, our curried function finally has both pieces of the puzzle.
Yes, now it can do the work.
It takes the number from the list, pulls the trap 2 out of its amber closure, performs the evaluation, and just tells filter whether to keep the item or throw it away.
It is just an incredibly elegant way to configure generalized functions into highly specialized tools on the fly. And you do it without needing to write custom loops for every possible scenario.
So our pipeline has now mapped the data to integers, and it's filtered out the odd numbers. The final stage is finding the largest remaining value. The lab has us write a simple comparison function called larger, and then introduces the reduce function to arrive at our final answer, largest.
And reduce is such a powerful tool. If map transforms data 1-to-1 and filter removes data, reduce is all about folding data down into a single summary value.
I always picture it like folding a massive sheet of paper in half repeatedly.
That's a great visual.
You take the first 2 numbers in the list and apply your comparison function, Whichever number is larger survives. Then you fold in the next number from the list, comparing it against your current survivor. You keep folding the list into itself over and over, carrying that accumulating survivor forward until you are left with one single thick square, the absolute largest number in the data set.
And that accumulating survivor is literally called the accumulator in functional programming terms. Manages the state of that accumulator for you, stepping through the collection without you ever having to write an explicit loop counter.
So we have all these discrete, highly testable pieces of logic now: round all, even all, and largest. The lab then requires us to use the comp function, which stands for composition, to stitch them all together into one unified pipeline called final result.
Yeah, the comp function acts as the plumbing. It connects the output of one transformation directly into the input of the next. But, and this catches a lot of people off guard, it operates with a specific directional flow that mirrors mathematical notation.
You're right.
In mathematics, if you write the equation f g x, the function closest to the data, the inner function g, evaluates first.
Meaning that in Clojure, the comp function actually reads right to left.
Correct. The data enters the composition from the right side. If your composed pipeline is defined as largest, then even all, then a round all reading left to right in the code, the raw data actually hits round all first on the far right.
Oh, wow.
Yeah, and then those rounded results flow leftward into even all, and those filtered results flow finally into largest.
It definitely takes a minute to mentally adjust to right-to-left data flow when you're just reading the code on the screen, but the mathematical purity of it is brilliant. It creates a sterile, perfectly predictable environment where data flows cleanly from one end to the other.
It really does.
But comp gives us this beautiful, pristine pipeline, but a pipeline is entirely useless if there's no water flowing into it. Hard-coding a vector of numbers is fine for a sterile test, but real-world programs have to talk to the chaotic outside world.
They absolutely do.
So how do we pipe messy data from an external file system into this functional environment?
Which brings us perfectly to part 2 of the lab. We break out of the closed system and introduce I/O input-output operations.
The mission here is to extract data from an external file called data.txt and convert it into a workable list of double values. And the lab points us toward 3 specific functions to achieve this: slurp, a string splitting function, and double parse double.
Can we just appreciate slurp for a second?
It is the best name.
It is one of the most vividly named functions in any language. You point it at a file path, and it simply opens the file, reads every single byte, and pulls the entire contents into memory as one giant string.
Just slurps it right up.
Exactly.
So once we have that massive string, we use Clojure.stringSplitLines to chop it up based on the line breaks, which gives us a collection of individual strings. But those strings still need to be converted into mathematical numbers.
Right.
This is where double parse double comes in, and to anyone who has written Java, that syntax looks incredibly familiar.
Well, because it is literally Java. Clojure is designed to run on the Java Virtual Machine, the JVM. The creators of Clojure realized there was no point in rewriting decades of highly optimized, battle-tested Java libraries for things like string parsing or network protocol.
Why reinvent the wheel?
Exactly. So Clojure allows you to seamlessly reach down through the functional layer and invoke underlying Java methods whenever necessary. It is a wildly pragmatic design choice that gives Clojure immense industrial power.
So we now have our working list of doubles pulled dynamically from the file system. The lab asks us to run some basic aggregations, counting the values to get numCount, summing them up for numSum, and calculating a mean. And it introduces us to the conj function to help manage our collections.
Ah, conj.
Yeah, the instructions show a very specific behavior. If you have a list containing the numbers 6, 12, and 4, and you use conj to add a 0, the result is a list where the 0 is at the very front. 0, 6, 12, 4.
Conj, which is short for conjoin, is the standard way to add an element to a collection in Clojure.
Wait, hold on. If I'm adding an item to a list, my human instinct says to append it to the end. If I'm joining a line of people at the grocery store, I don't just shove my way to the front, I go to the back.
Hopefully, yeah.
If Kanjan puts the new item at the front of the list, it means Clojure is pretending rather than appending. Why design the language to operate backwards compared to human intuition?
It's a great question. To understand this, we have to look beneath the functional syntax and examine how the memory is physically architected. In Clojure, standard lists are implemented as singly linked lists.
Okay, let's picture the physical memory allocation here. In a traditional Java array, a list of numbers is like a train with cars bolted onto a single rigid track. The system knows exactly how long the track is, and the memory is contiguous.
Exactly. But a linked list operates on entirely different physics. The data isn't contiguous. Each piece of data is an independent train car floating in memory.
So they aren't bolted together on a track.
No. The only way the list stays together is that every car holds a pointer, a directional arrow aimed directly at the car behind it. Car 1 points to car 2. Car 2 points to car 3.
So if each piece of data only knows about the single item right behind it, finding the end of the line means you have to start at the front and physically walk past every single item, following the pointers one by one until you finally hit the caboose.
Yep.
If my data set has 1,000,000 items, that's 1,000,000 distinct memory operations just to find the spot where I can attach a new number. That is a massive performance hit. It's an order in operation just to append one value.
Exactly. The larger the list grows, the slower the append operation becomes.
Yeah.
It's wildly inefficient. But what happens if you want to add a new car to the front of the train?
Oh, you don't have to walk the list at all.
No.
You just take your new piece of data, point its arrow at the current front of the train, and declare, I am the new engine.
Exactly. It takes exactly one operation. It is computationally instantaneous, an order of one, regardless of whether the list contains 10 items or 10 billion items.
Wow. So by forcing Clojure to prepend to linked lists, Clojure isn't just being quirky. It is aggressively enforcing algorithmic efficiency. It physically prevents us from writing a casual line of code that accidentally grinds the system's memory to a halt as our data sets scale up.
And that is the profound value of understanding the underlying data structures. When you know why a language behaves a certain way, you become a far more capable engineer. You stop fighting the language and start leveraging its architecture.
It's brilliant.
It is. And incidentally, if you ever truly need to append data efficiently in Clojure, you simply use a vector instead of a list, because vectors utilize a completely different memory structure. Kanji is actually polymorphic. It's smart enough to prepend a list for efficiency, but it will append to vectors.
That structural intelligence is phenomenal. So we calculate our final mean from the file data, which comes out to 86.365 for the sample set, by the way, and our local script is completely functional. But as the saying goes, code doesn't exist until it is safely secured in version control.
Absolutely true.
A working script on a local laptop is incredibly fragile. So the lab concludes by requiring a specific submission workflow utilizing Git version control.
Yeah, and we need to talk about those specific commands.
Right. We run our standard commands to stage the files git add and commit the changes with a message. Git commit the semlab code updated. That creates a snapshot in our local history.
Standard stuff.
But the critical requirement for submission is utilizing git tags before we push to the remote server. We don't just push the code. We attach a permanent name tag to this specific commit, marking it as our official lab submission.
Using git tag, a lab will end submission 1 meter lab completed. And it's important to understand why the course mandates this specific workflow. They are training you in the concepts of release engineering.
Okay, what does that mean in practice?
Well, in a professional repository, you might have dozens of developers making hundreds of commits a week. The commit history is a chaotic, rolling river of minor changes, bug fixes, half-finished features.
Just a constant stream of updates.
Right. And when a software company decides to ship version 2.0 to their customers, they can't just point to the rolling river and say, hey, use whatever code was there on Tuesday afternoon. The code base is just too fluid.
So you create a tag. It acts like a hardened save state in a video game right before a major boss fight. It completely freezes that exact configuration of the code in time.
Exactly. By tagging your lab submission, you are creating an immutable artifact. The instructor can grade that specific save state, and it doesn't matter if you continue experimenting and breaking your local code the next day. The tagged release remains perfectly intact.
And then you just use git push follow tags to send it all up, and you wait for that automated email receipt.
It's the difference between keeping a messy diary of your daily work and publishing a finalized novel. Tagging is how we publish in the software engineering world.
We've covered immense technical ground today. We took abstract functional theories and built a tangible purification pipeline using map, filter, and comp. We dealt with the friction of pulling raw data from the external file system using JVM interop. We explored how memory pointers dictate the efficiency of linked lists, and we utilized release engineering concepts to secure our final artifact.
It's a lot to take in, but if we synthesize the underlying theme of this lab, it is really about the structural shift from imperative to declarative problem solving.
Yeah.
In older paradigms, you write loops. You micromanage the iterator, you mutate temporary variables, and the actual business logic, what we are trying to achieve, gets buried under the mechanical noise of how we are iterating through memory.
You literally lose the forest for the trees because you're too busy managing the loop counter.
Exactly. By extracting the iteration logic away from the developer, functional programming elevates the code. When you use map and reduce, you are no longer writing loops. You are defining independent mathematical transformations.
And the resulting pipeline is predictable.
Yes, it lacks hidden state mutations, and it is incredibly legible. You can look at a composed function and instantly understand the architectural flow of the data without having to mentally decode a nested for loop.
We took the theory, we started the engine, and we successfully flew the plane. We built an elegant, working data pipeline.
We survived the flight.
We did. To wrap up this deep dive, we want to leave you with a final, lingering thought to explore as you continue your journey into functional programming. We've seen how Comp creates a beautifully predictable pipeline where data flows cleanly from one end to the other. We tested this by slurping up a static finished text file.
Right, data.txt.
But consider this scenario. What happens when your data source isn't a static file that you can read from beginning to end? What happens when your data is a continuous, infinite stream of chaotic events like live user interactions on a global application or thousands of financial market ticks coming in every second?
Oh, that changes things.
How do these rigid, elegant, functional pipelines adapt when the river of incoming data never actually stops flowing? How do you map or reduce a collection that literally has no end?
That is a phenomenal architectural puzzle to consider.
Thank you for taking this deep dive into Clojure with us. The theoretical concepts are powerful, but the true mastery of this paradigm shift only happens when you face the friction yourself. Open your terminal, fire up the REPL, and start building. Catch you next time.